Current electricity. Electric current is the flow of electric charge. In solid conductors, electrons carry charges into the circuit because they are free to move around the atomic networks. Protons are bound inside the atomic nucleus, locked in fixed positions. In fluids such as electrolytes in car battery, positive and negative ions as well as electrons can flow. Electric current is measured in amperes, abbreviated with the symbol capital A. An ampere is the flow of 1 coulomb of charge per second. When current is flowing, negative electrons move through the atomic network of positively charged atomic nuclei. So an electric current is the rate of flow of charges through a conductor. The amount of current flowing through an electric device or circuit is measured with an ammeter. Here's a diagrammatic representation of a simple circuit consisting of a battery, an ammeter, and a load, in this case a bulb. An ammeter is a device of low resistance and thus is usually connected in series with other devices. Let us see how we use an ammeter. For this we need wires, bulb, ammeter, and a switch. We will connect the circuit as it was in the diagram. Now that the circuit is connected, we will switch it on. You see the bulb glows. That means current is flowing, and the ammeter reads 0.3 amperes. The unit of current is amperes, named after French scientist Henri-Marie Ampère. Now we will connect 4 dry cells instead of 2 and see what happens. You see that the bulb is brighter and the reading on the ammeter is 5 amperes. So there is an increase from the previous reading. Notice also that the dry cells are connected in series to make a battery. Potential difference. Charges will not flow unless there is a potential difference, also called a voltage difference. Voltage is related to potential energy. It is the electric potential energy per charge. The unit of voltage is the volt. Electric engineers and electricians often think of voltage difference as an electric pressure that pushes charges through a circuit. Something that provides voltage difference is known as a voltage source. Batteries and generators are capable of maintaining a continuous flow of electrons. In a battery, a chemical reaction releases electrical energy. The electrical potential energy produced is available at the terminals of the battery. The voltage provides electric pressure to move charges between the terminals in a circuit. There is often confusion between charge flow through a circuit and voltage being impressed across a circuit. Charges flow through a circuit because of voltage across the circuit. We do not say that voltage flow through a circuit. Voltage don't go anywhere. It's the charges that move. Voltage causes current. In general, the potential difference between 2 points, say A and B of a conductor, is defined as the work done in moving a unit of charge from point B to A of the conductor. Potential difference is equal to work done in joules over the charge moved Q in coulombs. VAB is equal to W over Q. This potential difference is measured using a voltmeter. Here's a diagrammatic representation of a circuit consisting of a battery, a bulb, a voltmeter. In this case, we are measuring the potential difference of voltage across the bulb. A voltmeter is a device of high resistance and is thus connected in parallel with other loads or devices. Let's see how we measure the voltage in a circuit. We will use some wires, a bulb, a voltmeter, switch and dry cells. Note that the voltmeter is connected in parallel to the bulb here. We will first connect two dry cells to the circuit and see the potential difference. The voltmeter reads 1.9 volts. Now connect the three cells. The bulb glows brighter and the voltmeter reads 2.6 volts, which is higher than the previous reading. So the potential difference increases when we add the batteries. In other words, the amount of current flowing through 2 points in a circuit depends on the potential difference applied between the 2 points in the circuit. Points at the same electric potential. The two voltmeters V1 and V2 on your screen indicate the same reading. This is because a good conductor of electricity joins points A and D. The same applies to point B and C. Points A and D are said to be at the same electric potential, and so are points B and C. Each of the voltmeters V1 and V2 therefore measures the potential difference of voltage between points A and B. That the electric potential at A is higher than that at B, and therefore the conventional current flows from point A to B through an external circuit, that is the bulb. Current and voltage in series arrangement. These bulbs and ammeter are connected in series. When the circuit is connected and completed, it is observed that the readings on the ammeters is the same. Therefore, in a series connection, current is uniform, that is A1 is equal to A2 and is equal to A3. Now we want to measure the potential difference across each of the bulbs. Notice that the voltmeter is connected in parallel to each of the bulbs. When the circuit is complete, it is noted that the voltage across each of the bulbs is different. However, the total voltage drop across the bulbs, that is V1 plus V2 plus V3, will be equal to the total voltage V4 across the terminals of the battery. In conclusion, in a series arrangement, the same current flows through each component, but the sum of the voltage drop across the component is equal to the supply voltage. Therefore, in a series connection, A1 is equal to A2 and is equal to A3. At the same time, V1 plus V2 plus V3 is equal to V4. Current and voltage in parallel connections. Now these bulbs are connected in parallel to each other, and an ammeter is used to record the current flow through each of the bulbs. When the circuit is complete, it is noted that the ammeters record different readings. However, it should be observed that A1 plus A2 plus A3 will be equal to A4. When we take the voltage across each of the bulbs, it will be noted that the voltage reading on all the voltmeters is equal. That is, V1 is equal to V2, it's equal to V3, and is equal to V4. In conclusion, when components are connected in parallel, the sum of the current in the circuit is equal to the total current. Thus, the total current flowing into a junction equals to the total current flowing out. 2. There is equal voltage drop across each of them since their terminals are at the same electric potential. Ohm's law. The relationship between voltage across a conductor and the current flowing through it is summarized in Ohm's law, and it is as simple as it goes. If you switch on these torches, you realize that the yellow one lights, but the red one doesn't. And you know why? That's because the yellow torch has dry cells inside. These dry cells supply the voltage needed to drive the current through the conductor, and thus the bulb lights. We can set up a simple activity to help us understand the relationship between current I flowing through a circuit and the potential difference V. Observe the difference in the intensity of the glow when different cells are introduced in the circuit. You see that the intensity increases as the number of cells increase. So the larger the voltage, the larger the current. We can establish the relationship between voltage and current by connecting a cell, an ammeter, a voltmeter, a resistor, and a rheostat. Switch on the circuit and drag the pointer of the rheostat to vary the current flowing through the circuit. Each time you drag the rheostat pointer, record the readings of the ammeter and the corresponding voltmeter. Once you have a couple of ammeter voltmeter readings, plot a graph of voltage against current. The graph obtained is a straight line that passes through the origin. Voltage is therefore directly proportional to current. The gradient of the graph, that is change in voltage over change in current, is a constant. The constant is called resistance of the wire used. Thus, resistance R is equal to voltage V over current I. The SI unit of resistance is the ohm. This observation is known as Ohm's law, which states that the current flowing through a conductor is directly proportional to the potential difference across it, provided temperature and other physical conditions are kept constant. A simple way to remember Ohm's law is to visualize a triangle VRI. To find any of the variables, simply hide that variable and you get its formula. So when we hide V, we get R times I. Similarly, if we hide R, we get R is equal to V over I. And if I is hidden, we get I is equal to V over R. Electrical resistance. So the amount of charge that flows in a circuit depends on the voltage provided by the voltage source. The current also depends on the resistance that a conductor offers to the flow of charge, the electrical resistance. Electrical resistance is the opposition offered by a conductor to the flow of electric current. It occurs when a charge flowing through a conductor has its movement impeded by collisions with the atoms and impurities in the conductor. These collisions scatter the charges, leading to the loss of their momentum and energy in form of heat. A material with high conductance has very low electrical resistance, like copper. The instrument used for measuring resistance is called the ohmmeter. The resistance of a wire depends on the conductivity of the material of the wire and on the thickness and length of the wire. Thick wires have less resistance than thin wires. Longer wires have higher resistance than short ones. Electrical resistance also depends on temperature. For the most part, increase in temperature means increased resistance because heating increases the vibrations of atoms and thus increases the collisions per cross-section of the conductor. Let us look at the conductivity of a material. Experiments show that resistance R of a uniform conductor of given material is directly proportional to its length. That is, R is proportional to L. Therefore, resistance R is equal to constant times length. That is equation 1. So for a given conductor, R over L is equal to a constant. As the length of a conductor increases, so does the resistance. The resistance of a wire is inversely proportional to its cross-section area, A. Thus, R is proportional to 1 over A. A conductor with a larger cross-section area has many free electrons for conduction and hence better conductivity. From the foregoing, resistance times cross-section area is equal to a constant. Equation 2. For a given conductor, therefore, Ra is equal to a constant. Note that if the conductor has a circular cross-section, A is equal to pi r squared, where r is the radius of the wire. But then r is equal to d over 2, where d is the diameter of the wire, and therefore A is equal to pi d squared over 4. Hence, rd squared is equal to a constant. Combining equation 1 and 2 for a conductor with uniform cross-section area, resistance is equal to a constant times length over area. That is, R is equal to rho times L over A, where rho is constant and is the resistivity of the material. Hence, rho is equal to AR over L. The resistivity of a material is numerically equal to the resistance of a sample of the material of unit length and unit cross-section area at a certain temperature. The unit of rho is the ohmmeter. The resistivity of a material is dependent on temperature. For metal conductors, it increases with increase in temperature, while semiconductors, it decreases with increase in temperature. Note that it is helpful to express all the lengths in meters so as to obtain resistivity in ohm-meter units. Resistance. A resistor is a material which offers resistance to the flow of current. Resistors are broadly classified as fixed or variable resistors. A fixed resistor can be a wire like nichrome or a carbon resistor. Its resistance is fixed as the name suggests. A variable resistor have varied ranges of resistance. They include rheostats, potentiometers, and thermistors. This is a rheostat. It has 3 connections here, here, and here. It has a sliding contact connected to the first connection. It consists of a long coil of wire. The length of the wire between here and here is 0 and hence no resistance. When you move the sliding contact, you are basically increasing the length of the conductor and hence the resistance. This is a simple circuit that has 3 batteries in series, a switch, a rheostat, ammeter, and a bulb. Now we use the rheostat as a variable resistor. The switch is closed. In this position, resistance is 0, current is maximum, and the bulb lights very bright. As I slide the contact, resistance increases, current goes down, and the bulb glows dim. Measurement of resistance. The first method of measuring resistance is the one we used in demonstrating Ohm's law. By taking various ammeter readings and corresponding voltmeter readings and using that to plot the graph of V against I, one can get the resistance of any material by simply calculating the gradient of the graph. The Wheatstone bridge method. The Wheatstone bridge is an arrangement for measuring unknown resistance. It consists of 4 resistors of resistance P, Q, R, and S connected together to form a quadrilateral or a bridge A, B, C, D. The pair of opposite junctions B and D is connected through a galvanometer, and the other pair of opposite junctions A and C is connected through a battery and a switch. If the resistances of the 3 resistors in the bridge are known, then the bridge can be used to calculate the resistance of the 4th resistor. Let us see how a Wheatstone bridge is used to calculate resistance. First, we will have to balance the bridge. The value of the resistors P, Q, R, and S are so adjusted that the galvanometer shows no deflection when the switch is on. This means that no current is flowing in the arm BD, and therefore the potential at B is equal to the potential at D. The bridge is said to be balanced. P over Q is equal to R over S. Knowing the value of the 3 resistors P, Q, and R, the unknown resistance S can be found out. S is equal to RQ by P. The meter bridge method. A meter bridge works on the same principle of the Wheatstone bridge. It consists of 1 meter long wire of constantan or manganese which is mounted on a wooden board. This wire has a uniform cross-section throughout its length. The meter bridge is mostly used to calculate the resistance of a given resistor to determine unknown resistance. The meter bridge is connected to the unknown resistance S and also to a variable resistor as shown on the diagram. A jockey at one end of the galvanometer is made to slide on the meter bridge wire. With this jockey, we search for a point on the bridge which corresponds to a null point. A null point is a point where the galvanometer shows no deflection and the bridge is balanced. When the bridge is balanced, the ratio of the resistance of wire AB to the resistance of the wire BC will be equal to the ratio of the resistance R to that of S. That is, P by Q is equal to R by S, or S is equal to QR by P. If ρ is the resistivity and alpha the area of cross-section of the meter bridge wire, then S is equal to ρ into 100 minus L by alpha, and P is equal to lambda L by alpha. Therefore, by knowing the balancing length L and the known resistance R, we can calculate the unknown resistance S. Resistors networks. Generally, in an electric diagram, a zigzag line represents a fixed resistor. Two thick dots at the ends represent brass terminals. In an electric circuit, resistors can be connected in series or in parallel. Resistors in series. Resistors are said to be connected in series if they are connected one after the other in the form of a continuous chain as shown here. Let us now calculate the effective resistance of the circuit. Consider three resistors R1, R2 and R3 connected to a battery through an ammeter. Observe the multimeter reading when it's used to measure the potential difference across R1, R2 and R3. Now observe the multimeter reading when used as an ammeter. You observe that the current flowing through R1, R2 and R3 is the same, and that the potential difference V1, V2 and V3 across R1, R2 and R3 are different. Let V1, V2 and V3 be the potential drop across R1, R2 and R3 respectively. Under ideal conditions, potential drop across resistors is equal to the sum of individual drop in potentials, that is, V is equal to V1 plus V2 plus V3, where V is the total potential drop. Now let us calculate the effective resistance using Ohm's law. Ohm's law states that R is equal to V over I. In a series circuit, the potential drop across each resistor varies. Hence, we calculate the potential drop V1, V2 and V3 across the resistors R1, R2 and R3. The total potential V is equal to V1 plus V2 plus V3, but V is equal to IR. Therefore, IR is equal to IR1 plus IR2 plus IR3. R is equal to R1 plus R2 plus R3. Therefore, the effective resistance of the circuit is equal to the sum of the resistances of the individual resistors in the circuit. Potential divider. Resistors connected in series can be used as a potential divider or a voltage divider. Consider two resistors connected in series with a battery of negligible internal resistance, as shown here. Such an arrangement is called a potential divider and is used in most of the electronic circuits. For the normal working of a transistor as an amplifier or as an oscillator, we may require a voltage less than the voltage of the battery in the circuit. In such cases, we make use of this voltage divider circuit. Let us see how the voltage is divided. The current flowing through the circuit is given by I is equal to V over R1 plus R2. The potential difference across resistor R1 is V1 and that across R2 is V2. V1 is equal to IR1, which is equal to V over R1 plus R2 times R1, equation 1. V2 is equal to IR2, which is equal to V over R1 plus R2 times R2, equation 2. Therefore, V1 over V2 is equal to IR1 over IR2, which is equal to R1 over R2, equation 3. The equation 3 shows that the potential difference across a resistor is directly proportional to the resistance. That is, if R2 is smaller compared to R1, then the potential difference across R2 will be small. Resistors in parallel. Resistors are said to be connected in parallel if they have a common positive terminal and a negative terminal as shown here. Let us calculate the effective resistance of the circuit. Consider three resistors R1, R2 and R3 connected such that the resistors have common positive and negative terminals as shown here. The resistors are connected to a cell through an ammeter. Observe the multimeter reading when used to measure potential difference across R1, R2 and R3. Now observe the multimeter reading when used as an ammeter. You observe that the current flowing through R1, R2 and R3 is different, and that the potential drop V1, V2 and V3 across R1, R2 and R3 is the same. Let us now calculate the effective resistance of the circuit. Let I1, I2 and I3 be the current flowing through the resistors R1, R2 and R3 respectively. Under ideal conditions, I is equal to I1 plus I2 plus I3. According to Ohm's law, R is equal to V over I. In a parallel circuit, the current flowing through individual resistors varies, and hence we first calculate I1, I2 and I3. Total current I is equal to V by R. I is equal to I1 plus I2 plus I3, or V over R is equal to V over R1 plus V over R2 plus V over R3. V into 1 over R is equal to V into 1 over R1 plus 1 over R2 plus 1 over R3. Cancelling out V, 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Consider two resistors R1 and R2 connected in parallel as shown here. The potential difference across each resistor is the same. V is equal to I1 R1 and it's equal to I2 R2. Total current I is equal to I1 plus I2. The potential difference across the parallel combination of R1 and R2 is also V. The effective resistance R1 and R2 connected in parallel is Rp. 1 over Rp is equal to 1 over R1 plus 1 over R2. Rp is equal to R1 R2 by R1 plus R2. V is equal to I1 R1 and it's equal to I2 R2, which is equal to I Rp. I1 R1 is equal to IRP and it's equal to R1 R2 by R1 plus R2 times I. I is equal to R2 over R1 plus R2 times I. Similarly, I2 is equal to R1 over R1 plus R2 times I. That is, current through one branch is equal to resistance of the other branch into the total current divided by the total resistance. This is called current division law. Example: two resistors of 6 ohm and 3 ohm in parallel are connected in series to a 4 ohm resistor and a cell of EMF 1.5 volts. Calculate the equivalent resistance of the circuit and the current through each of the resistors. In the solution, resistance of AB is equal to 6 times 3 over 6 plus 3, which gives us 2 because the two resistors are connected in parallel. Now we shall have the combined resistance, which gave us 2, is connected in series to the 4 ohm resistor, and therefore the equivalent resistance is 2 plus 4, which gives us 6 ohms. B. Total current flows through the 4 ohm resistor. Therefore, IT is equal to VT over RT, which is equal to 1.5 over 6, which is equal to 0.25 amps. Now, IA plus IB is equal to 0.25. Using the current divider law, IA is equal to RB over RA plus RB times I, which is equal to 3 over 9 times 0.25, which gives us 0.83 amperes. Similarly, IB is equal to RA over RA plus RB times I, which is equal to 6 over 9 times 0.25, which gives us 0.167 amperes. Electromotive force and internal resistance. We saw in Form 1 that when unlike charged particles are separated, a potential difference is created. Electromotive force is the potential difference measured in volts. The symbols commonly used for electromotive force are E or V. The potential difference in charges forces current to flow. There are practically 7 forms of electricity generation, and all of them create an electromotive force or EMF. The potential difference across 2 open terminals is known as the unloaded voltage and is equal to the electromotive force of the cell. This EMF forces current to flow when a circuit is attached to the source of EMF. There is typically some amount of resistance in all electrical components and devices. When current flows, the voltage across the terminals of the source of EMF is no longer the unloaded value. There will be a voltage drop inside the device due to the internal resistance of the EMF source. When the circuit was not connected, the battery had an unloaded voltage reading of 1.5 volts. Once the circuit was connected and current started to flow, there was a voltage drop across the internal resistance of the device, and the applied circuit voltage was reduced to 1.3 volts. The DC power supply is a commonly used device in the lab. It has the ability to create different amounts of EMF. As the voltage is increased, the potential difference between the terminals is increased. Note that the unloaded voltage of the power supply is set to 5 volts. A DC power supply will experience a loss of potential difference due to internal resistance of the power supply. When the circuit is connected and the current starts to flow, the internal resistance of the power supply reduces the applied circuit voltage to 4.7. This difference of 0.3 volts is called the lost volts. Relationship between EMF and internal resistance. If a resistor R is connected in series with a cell as shown on your screen, the internal resistance of the cell R is considered to be connected in series with the external resistor R. The current flowing in the circuit is therefore given by the equation: current is equal to the EMF over the total resistance. I is equal to E over R plus R, where E is the EMF of the cell. Thus, E is equal to I into R plus R, which is equal to IR plus IR, which is equal to V plus IR. IR is the voltage drop across the external resistor R, while IR is the voltage drop across the internal resistance. The voltage across the external resistor is called the terminal voltage. while the potential difference drop across the internal resistance is called the lost voltage.
The Royal Institution in England had very quickly, in the early 1800s, devised a very large bank of batteries. In fact, the batteries consisted of 2,000 cells. If these cells produced each about 0.7 of a volt, you can imagine even 2,000 of those connected in series would have given quite a large amount of electric current. Michael Faraday started experimenting with this new form of energy. And it wasn't long, as one can imagine, before all sorts of discoveries were made. Oersted realized very quickly that if an electric current was passed through a wire, that a magnetic field could be generated. Michael Faraday realized that if you took one piece of wire and you laid it parallel with another, passing current through one of the wires, induced by not physical connection but by electromagnetic connection, induced a voltage in the wire lying parallel to the first one.